Okay, welcome back. This is the discussion for 10.7, which is partial fraction decomposition, everybody's favorite. It is important when you get to calculus, if you're going to be an engineer, if you're going to do whatever, anything in calculus or past calculus, partial fraction decomposition actually becomes very powerful when you're dealing with more difficult things. So here it is, let's dive into it. There's only 4 or 5 homework questions, but we'll do 2 of them. So let's look at number 1. Number 1 says find the partial fraction decomposition of 9 over x minus 3, x plus 6. Okay. So it's first important to know that you would have to break this up into some constant over the x minus 3 factor plus some constant over the x plus 6 factor, right? And I have an equation, right? The left-hand side has to be equal to the right-hand side, because if I were to add the right-hand side together, I would get the left-hand side, right? Now, we just need to figure out what a and b will make this work, right? So what I would do at this point is multiply everything by the lowest common denominator, which is this x minus 3 times x plus 6. So if I multiply the left by x minus 3 and x plus 6, and then I'll multiply the right by it and distribute to both terms. So x minus 3, x plus 6 here, and x minus 3, x plus 6 here. Okay. So what happens is on the left-hand side, x minus 3 cancels the x minus 3, x plus 6 cancels x plus 6, and I'm left with 9. The right-hand side, the x minus 3 cancels the x minus 3 on this a term, leaving me with a times x plus 6. X plus 6 cancels with the x plus 6, leaving me with b times x minus 3. And this has to be true. For this entire thing to be true, this has to be true for every single x. 9 has to be equal to all of this junk over here, right? And therefore, I can come in and say, hey, what happens if I let x equal something like, say, negative 6 for a minute? Right? Why negative 6? Because negative 6 plus 6 is 0. And if I have a 0, that thing disappears, and that's very nice, right? So I'll say, what happens if x is negative 6? My equation becomes 9 equals negative 6 plus 6 is 0, so this whole term is gone by negative 6 minus 3, that's negative 9, times b. How very convenient, b is negative 1 when I divide each side by negative 9. Okay, done with that. The next thing that I'm going to do is say, hey, that was very awesome. What happens if I let x equal 3 to eliminate this crap over here? So I will. What happens when x equals negative 3? I bet goodness. If x is negative 3, I still have the equation 9 equals, negative 3 plus 6 is still 3, so that's 3a, plus, well, negative 3. I don't want it to be negative 3, I'm sorry, I want it to be 3, because I want 3 minus 3 to be 0. So I have 3 plus 6 is 9a. 3 minus 3 is 0, that zeroes out, so it's gone. Oh, look at that, how nice is that? A has to be 1. And I have it. So in the end, if a is 1 and b is negative 1, what I'm really saying is that the fraction (9 over x minus 3 times x plus 6) can be decomposed into the difference, because b was negative, of these two fractions. That's what we're looking for here. Okay, good. That was number 1. The other one that was asked was number 5. I think 5 is the big, hideous one. Yeah, a little bit. So let's do it. Five, same question, the complete, oh, just kidding, I lied. Well, I mean, sort of. The complete partial fraction decomp of this expression, x minus 5, over x squared minus 3 times x plus 1 squared. Okay. So when we write this, if ignoring the A, B, C, D, possibilities here, if I wanted to decompose this, I have to consider this x squared minus 3 could be one of the denominators, but I also have to consider the powers of these denominators. This is a second degree polynomial in the denominator that I can't factor anymore. And so since it's a second degree, its numerator could possibly be a first degree polynomial still. And so I have to consider that it's one less power, it might be ax plus b, right? The other factor here is x plus 1, but there is two factors, it's x plus 1 squared, and so I have to consider that I might have had an x plus 1 squared in my initial sum of a bunch of fractions, but I might also have had something just over an x plus 1 to the first power, right? Because the common denominator here still ends up being this guy over here. But the nice thing is by breaking x plus 1 squared into x plus 1 squared and an x plus 1 is that I don't have to worry about having that first degree polynomial in the denominator here. If I did have a first degree polynomial, I could simplify that, or I could break it down more. And therefore all I have to worry about is a constant over these terms, right? So this ax plus b, this polynomial appears because this is not reducible and it's not a repeated power of another factor, right? So our answer should look like this. It may be in different order, right? It could very well be a over x plus 1 squared plus b over x plus 1 plus cx plus d over x squared minus 3. It doesn't matter, right? It's a constant over an x plus 1 squared, a constant over an x plus 1, and then a constant x plus another constant over my x squared minus 3. So pick the one that looks like. That looks like b to me. So anyway, that. And it's important for the rest of the problem to write it in the way that they've written it. So I'm going to, and they wrote it like this top one. So we'll solve this top one because when I say a is this, b is this, they're specifically talking about a, the coefficient in front of the x on this specific fraction. So that's what we want to do. To solve this, I'm going to treat it the same. I'm going to multiply everything by this denominator right here, this big boy. X squared minus 3, x plus 1 squared. I don't need an x plus 1 squared and then another x plus 1. That x plus 1 squared is going to handle the x plus 1 over here. And so that's what I do is I multiply everything by x squared minus 3 and by x plus 1 squared. So here, x squared minus 3 multiplied by x plus 1 squared. And here, x squared minus 3, x plus 1 squared. This is going to get a little messy. Mostly because I'm working on the limitations of this smaller board. It'll clean up a little bit nicely though. The x squared minus 3, the x plus 1 squared gets all canceled out by that, and I'm left with x minus 5. On the left equals, my x squared minus 3 cancels over here, leaving me with ax plus b multiplied by, I probably want to move this over. I might need the room. Multiplied by x plus 1 squared is left over. Plus, the x plus 1 squared gets canceled with the x plus 1 squared, and so I have c multiplied by x squared minus 3. Plus, the x plus 1 here only cancels out one of the x plus 1's there. So I have plus d multiplied by x squared minus 3 and x plus 1, right? Now you might be able to, with a little bit of forethought, see that d is going to be the hard one to solve for, because I can eliminate stuff. But every time I choose some nice little value, I'm always going to eliminate my d, right? That's going away. So it's also a little bit rough because even if I so desire to choose a horrific number like the square root of 3 in order to square it to get a 3 and minus a 3 to eliminate these two, right? I still have really ugly numbers here. So I'm going to abandon that nice convenient value of x thought that we had that was so nice in number 1, because it's going to turn out not great for us, right? So I'm not going to completely abandon it though. I'm going to start down that road because I do have a good, nice value what happens when x is negative 1, right? So if I say x is negative 1, what happens? On the left-hand side here, I get negative 1 minus 5 is negative 6. If x is negative 1, this term is 0, because negative 1 plus 1 is 0. This term is 0, and I'm left with negative 1 squared, which is 1, minus 3, which is negative 2, and c. So I can solve for c using that value, divide both sides by negative 2, and I get c is 3. Right? So I have one of my 1, 2, 3, 4 values, right? But again, to eliminate these guys and solve for anything else, I'd have to say, hey, what happens when when x is the square root of 3? That sucks. I don't like it, right? So instead, I'm going to write this somewhere. C equals 3. Right? And I'm going to expand the right-hand side. So that is to say, this x plus 1, I'm going to actually square it, and then multiply that all by ax plus b. I'm going to distribute my c's, I'm going to FOIL all of this, and just get one big ugly polynomial, right? So I'll do it step by step here, and I'll probably have to erase all of this. Well, here we go. The x plus minus 5 on the left is just fine. But here I've got this ax plus b multiplied by x plus 1 squared, which when I FOIL that out, I get x squared plus 2x plus 1. Plus, and I'll just distribute this c, so I get cx squared minus 3c. Plus, I'm going to leave the d out here and then just FOIL these guys. So I get d multiplied by x to the third plus x squared minus 3x minus 3. Okay? Just kind of a little bit by bit. The next thing I'm going to do is take this ax plus b and distribute it through my trinomial here. So I get ax times x squared is ax to the third. Ax times 2x is plus 2ax squared. Ax times 1 is ax. And then bx squared. And then 2bx. And then b. And then my plus cx squared minus 3c. And then take that, throw the d through, plus dx to the third plus x squared minus 3, plus dx squared minus 3dx minus 3d. Okay? It's big, it's ugly, it's equal to x minus 5 on the left-hand side. I'm going to erase a bunch of this. This looks like hell, sorry, but let's, and I hope that's big enough. But c is equal to 3. Let's not forget that. I'm going to write it off the screen, but it's still there. Okay. Now, what do I do with this big glob of crap, right? I'm going to reorganize it, and I'm going to write all of my x to the thirds together. And so I have, on the left, I still have this x minus 5. Right? But I'm going to write my x to the thirds together, so I have ax to the third and a dx to the third, right? And then my squares, I have 2ax squared plus bx squared plus cx squared. Am I writing up and off the screen? Yes, of course I am, because that's what I do. Plus dx squared. I think that's all of them. Yep, looks like it. And then I have a x. I'm just going to new line here, plus ax plus 2bx minus 3dx. And then the rest of them are no x's, so I have plus b minus 3c minus 3d. Okay. All right, now the reason I did this is because in my x to the third terms, I'm going to factor that x to the third. I'm going to factor it to the right because I like it that way. If I factor the x to the third, I'm left with a plus d. Okay, in the next one, my x to the seconds, all of those guys, I'm going to factor the x to the second off to the right. If I do, I'm left with 2a plus b plus c plus d x squared. If I do the same thing for my x terms, I'm left with a plus 2b minus 3d a plus 2b minus 3d, yeah. And then plus, that's b minus 3c minus 3d. Okay. Now why in the world did I go to all that trouble to do this? Well, because I like to do long, hard stuff, right? Nope. Because there's a idea here that if I have, let's say ax squared plus bx plus c is equal to, let's say, dx squared plus ex plus f, right? I have a polynomial on the left, I have a polynomial on the right. In order to say that these two things are equal, they have to be equal everywhere. And the only way that these two second-degree polynomials are equal everywhere is if a is equal to d, b is equal to e, and c is equal to f. They literally have to be the exact same polynomial in order to be the same everywhere. Because if they're not, at any point, there's going to be some difference between the two, and they won't be the same, right? So that's what I'm saying here, is that I have a polynomial on the left that is x minus 5. In order for this x minus 5 to be the same as this on the right-hand side, a plus d has to be 0. It has to match up the x to the third term on the left. A plus d has to be 0 because there is no x to the third term on the left. Likewise, the x squared term on the right has to match the coefficient of the x squared term on the left, which is 0 because there's not one there. So this has to be 0. The x term has to be 1. The coefficients a plus 2b minus 3d have to add up to be 1. And then all of this junk over here, this b minus 3c minus 3d, that's the constant terms without an x, that has to equal negative 5. Okay? So what does all of this mean? I have 1, 2, 3, 4 equations. Those equations are a plus d equals 0. I'm going to write it funny for a little bit, and then there's going to be an aha moment. The other one is 2a plus b plus c plus d equals 0. A plus 2b minus 3d is equal to 1. And then b minus 3c minus 3d is equal to negative 5. And if only I had some way to deal with a system of equations, like, oh wait a minute, that's what we just did, right? I can turn this into a matrix, I can use Cramer's rule, I can, I don't know, I can do whatever I want. But I have a system. I have a 4 by 4, right? 4 variables, I have 4 equations. I can reduce it because I happen to know that c is equal to 3. Right? Don't forget that. We already know one of our values, but it doesn't matter. If I didn't know it, I can just solve this system through matrix, reduced row echelon form, all that jibber jabber. However you want to do it, you can reduce this, right? So, how do we do it? Well, if it were me, I would know, well, c is equal to 3, and since I already know one of my equations, I can eliminate one of these. Or sorry, since I already know one of my variables, I can eliminate one of these equations because I only need a system of 3 by 3, right? So I'm going to take out, probably the one with the most crap in it. I don't need it, right? I just need this as long as I come in and say, hey, that negative 3c, negative 3 times 3 is a negative 9. And then I can create a better system here, a more simplified system by saying I have a plus d is 0, a plus 2b minus 3d is 1. Add this 9 to the other side, that gives you b minus 3d is equal to 4. And I've already reduced it just by knowing c out of that 4 by 4 terrible, yuck world into a 3 by 3, which is much easier, right? And I literally can choose whichever equation I want to just say, nope, get out of here. So choose the ugly one, choose the one with the big numbers, right? But I have this system. If I want to play with matrices, there's my matrix, right? I can RREF this pretty quick, right? Row 2 minus row 1 to eliminate that 0. Or I can use Cramer's rule. I can find D is equal to, pick a row, doesn't matter. D is 1 multiplied by 2 negative 3, 1 negative 3. Plus 0 times who cares? Plus 1 more times 1, 2, 0, 1. Right? which is 1 multiplied by -6 minus, but another minus goes +3, plus 1 times 1 minus 0, and so I have -3 plus 1, so my determinant is -2, that's not bad, I like it. Right. Get rid of a little bit of this here. dx, I'm going to go perhaps green. dx is the determinant where 0, 1, and 4 are put in place of the x, and then everything else stays the same. dx is nice because I have 2 zeros I can exploit. Go on that row, and your dx is simply 0 times who cares minus 0 times who cares plus 1 times 1, 1, 4, 2. What, sorry, went out of order with that right there, right? But that's just 1 multiplied by 1 minus 8. 1 minus 8 is negative, oh, are you serious? It's -7. Oh, I think that's right. Let me try x. X then would be 7 over 2. Let me just throw it in. Oh, by x, I mean a. So if a is 7 over 2, then we're on a good direction. If it's not, then I've botched it and I've wasted all of your time. So cross those fingers. And I'm right, so good. Good, good, good. All right. So, and so what I'm saying here is that then I'm calling this dx. I should probably call it dA because the variable is a, not x. And therefore a is that dA divided by d, which is -7 divided by -2. The negatives just cancel out, and you're left with 7 over 2. And that, I threw it in, that's the correct answer. So we're on a pretty good streak here, right? It's very unlikely that I did these two right and something in the past wrong, right? So let's just keep going then. I've got A, it's 7 over 2. Write this down because I'm so out of room, I'm just erasing some stuff here. DB is my next one. It would be 1, 1, 0. Replacing B's column with 0, 1, 4. And then 1, -3, -3. Again, exploit that 0, or exploit the 0 in this column over here. It doesn't matter, pick one. So I end up with 1 multiplied by 1, -3, 4, -3. Minus 0 times who cares, but then plus 1 multiplied by 1, 1, 0, 4. Right? So this ends up being 1 multiplied by -3 minus, but there's another minus, so it's plus 12, plus 1 multiplied by 4 minus 0. So I get 12 and -3, 9. Times 1 is still 9, plus 4, so I get 13, and therefore B is 13 over -2, or -13 over 2. When you're writing a fraction, throw that negative in front, so in the system it would be -13 slash, what way does the slash go with that? 2. Okay. Good. Let me try that one just to make sure, because these are, I mean, they're not awesome numbers. That was B is -13 over 2. Cross your fingers again because we're at like 50 million minutes into this. I don't want to start this over. And correct. Okay, great. That's 3. I didn't check C, but you know, I'm hoping. So let's do D. So D. 0, and then 0, 1, 2, 1, and then 0, 1, 4. Again, I'm just replacing D's column, this, with the 0, 1, 4. Again, lucky, I get 1, 0, 0. Exploit that crap. This is then 1 multiplied by 2, 1, 1, 4. Or 1 multiplied by 8 minus 1, and therefore it's 7. And therefore D itself is, it's terrible notation because D is both this variable and the determinant, but D, this variable, is 7 over negative 2, and therefore it's negative 7 over 2. Right? And that should work. Let me throw all of these in just for kicks and giggles. It would be a shame to have messed up on the last, trip to the finish line. I said A was right, I don't know what it was. B, I threw in was right. C, we're saying was 3. And then D, I'm saying is negative 7 over 2. Submit that, check it, and I'm right. Thank goodness, because if I had to erase this and re-record it, I don't know, maybe I wouldn't. No, I'm just kidding. I would, because I love you guys. Thank you, and we'll see you guys for the next one.